Exercise 1930 is saying if you start with benzene and you can use any other reagents, how can you make each of these molecules? And you can do that in more than one way sometimes, but you just want to make sure that you have a valid way. Now the reactions you want to know for this chapter are in this little chart over here. You'll recognize bromination, chlorination is very similar. You just replace the bromines with chlorines. You have nitration, sulfonation, FriedelCrafts alkylation, FriedelCrafts acylation. So those should all be familiar to you from the mechanisms that you learned. Now if you do nitration, you can reduce the nitrogen. So you can replace the bonds to oxygen with bonds to hydrogen. And you do that just by adding iron or zinc and then HCl. If you do alkylation, FriedelCrafts alkylation, you can turn that out. You now have a benzylic position. You can react that with N-bromosuccinimide, NBS, and heat, and that will put halogens, bromines, on that benzylic position. Or you can oxidize it. Now here they're doing it with potassium permanganate, KMnO4, sodium hydroxide and heat followed by acid, but you could just as well use chromic acid, so H2CR2O7 or HCrO4. So you could use either of those. Those are both from chapter 18 in conjunction with reactions in this chapter. And then just note that if you do end up doing the FriedelCrafts acylation and you don't want the carbonyl, you can reduce it using a zinc-mercury amalgam, hydrochloric acid and heat. So these are the reactions you want to know in the context of this chapter. Okay, so that's sort of our recipe book. You would want to have that in your mind. And the first step in trying to come up with a synthesis for these polysubstituted benzenes, these benzene rings with more than one branch on them, the first step is just to realize what recipes you're going to need to use. Now the bromine, that one's more or less straightforward. That's going to be Br2, and in that recipe they have AlBr3. That's fine. You could also use FeBr3. They both happen through the same mechanism, so either one you want to use. In the mechanism we used earlier, we used FeBr3, so just for the sake of consistency there, I'm going to use that as the catalyst. But if you used aluminum 3-bromide, then that is fine too. And then for NH2, we didn't learn one reaction to put NH2 on a molecule, but we did learn how to do nitration. That'll at least get the nitrogen there. And then if you do that, you can reduce that nitrogen with an iron or zinc in the presence of HCl. So those two reactions together will put that NH2 on the molecule. Okay, so we would have first nitric acid in sulfuric acid, and second, we would have to reduce that with either zinc or iron in the presence of HCl. Okay, so those are our recipes. Now let's think about the order that we have to do them in. Bromine is a weak deactivator. It's a halogen. So this bromine is a weak deactivator. And it is orthoparadirecting. The NH2 is a strong activator. It has those lone pairs there on that benzylic position, and there's no resonance pulling them away from the ring, so that's a strong activator. And if you're having trouble following me as I discuss these activators, deactivators, and directing effects, try going back to the video for exercise 1919 and previous videos to see where all this is coming from. We're building on that information. These strong activators are also orthopara directors. Okay, so when we think about the order we want to do these in, we could do it in either order, because notice the way that they're on the molecule is they're ortho. So whichever one we put on first, that's okay. We'll get, we will get the ortho product no matter what. We'll also get other stuff. We'll get the para products. That's a mess, but we can always separate the molecules through chromatography or whatever else. So, or distillation. So either one will work, and so long as it works, you'll get full credit on a test. But really, you'll want to think about what's most efficient. And here, if you put the bromine on first, that will make the ring less reactive, and it'll be a pain to put the second thing on. So it would be better if we put this activating group on first, and then it'll be really easy to put the bromine on. So we'll start with bromine, or we'll start with benzene, sorry, not bromine. We'll start with benzene. We'll do this first reaction first. We'll put the NH2 on first, so we'll make aniline. And the first step, of course, is HNO3, followed by H2SO4. That would give us, so if we do that, that would give us a benzene ring with a nitro group. If we treat that with zinc or iron in the presence of HCl, that would reduce that. The bonds to oxygen would become bonds to hydrogen. And then we can do the bromine. We can add the bromine. So we could add Br2 and FeBr3. Oops. So in that case, we would actually get two products. That's okay, so long as we get the product we want. We'll get the ortho product, and we'll also get the para product. Regardless of that, we get the product we want, which is the ortho product. So here, what we had to worry about is once we have this branch on this ring, this has a lone pair there, it's a strong activator, it's an ortho-para director, and so we'll get both the ortho product and the para product of adding the bromine. So long as we get that ortho product, we're getting what we want. And so that is a satisfactory synthesis for the molecule that they gave us, starting with benzene. So let's try doing the same thing. We can refer to our little tableau of our little recipe book of reactions here. So first, let's just decide what recipes we need to use. If we're adding a nitro group, then we're going to do nitration. We'll use nitric acid and sulfuric acid. So in order to put that on, we'll need to do HNO3 and H2SO4. For the chlorine, we'll do chlorination, so we'll add the Cl2 and the AlCl3. So the question is, which one should we do first? And what you notice here is that these are meta to each other. They're 1,3 away from each other. So they're meta to each other. The halogen, chlorine, is actually is weakly deactivating. It's a weak deactivator. And it is orthopara directing. The nitro group is a strong deactivator. But it is meta-directing. These two are meta to each other. And so we want to put the nitro group on first. So we'll start with benzene. In each one of these exercises, each one of the examples of these exercises, we need to start with benzene. We'll start with benzene, and we'll put the nitro group on first. HNO3, H2SO4. Now that's going to deactivate the ring, so doing this in a laboratory will be kind of a pain because this will take a while to react. But we will have our, let me put it here. You could put it anywhere. All of the positions on the benzene are symmetrical, but just so it matches the exercise, there's our nitro group. And that, although it's strongly deactivating, it is meta-directing. So if we then try to add the chlorine will add to the meta position. And so we end up getting our product. Notice that you would not be able to do the reaction in the other way. If you took the benzene and you reacted it with the chlorine first, so you put the chlorine on it first, the chlorine is orthoparadirecting. So if you try to put the nitro group on after that, you'd get two products. One would be the nitro group on the ortho position, and one would be the nitro group on the para position. And notice that because chlorine is orthoparadirecting, so neither of those is the product that we want. We want the meta product. And so you would not be able to do that synthesis. You have to add the nitro group first. And so this top synthesis is the one that would give you your desired product. Okay, for C. So we have our little recipe book that we would have memorized. And here, we want to think about, just at first, before we think about the order we have to add these in, let's just think about what recipes we need to do in order to add these things. Let's start with this top one, NH2. Well, we don't have a direct way to make NH2, but we could add NO2 onto the molecule and then reduce it. So we'll have two steps for that. First, we'll have HNO3 and H2SO4. That puts the nitro group on, NO2, and then you reduce that with either iron or zinc in the presence of HCl. So that's how we can make that branch there. The other branch, this one, is an alkyl branch, so that's FriedelCrafts. That's going to be a FriedelCrafts reaction. But a really important and kind of sneaky thing that you'd have to notice here is that this carbon is primary. Well, in this particular reaction, it's secondary, but let's think back to the reagent we would have to use in a FriedelCrafts reaction. Let's say you wanted to put this on. This is a new carbon-to-carbon bond that you're making, so it's FriedelCrafts, and in the case of FriedelCrafts, you use some alkyl halide and AlCl3, or you use an acyl halide and AlCl3. Let's see if we can do it with FriedelCrafts alkylation. With FriedelCrafts alkylation, you would have that same branch, but instead of attaching to benzene, it would be attached to your chlorine, and you'd have AlCl3. But remember the mechanism for this. And the mechanism for this, the chlorine leaves and you form a carbocation. And in the case of FriedelCrafts alkylation, that carbocation can rearrange. And in this case it would move over to the more stable secondary position. And so if you tried to do FriedelCrafts alkylation, you wouldn't have it attach in this way. You would have it attach like this, because the nucleophile will attack this electrophilic carbon. So you can't do FriedelCrafts alkylation because of that carbocation rearrangement. And if that's confusing to you, I would encourage you to go back and watch the video for the mechanism of FriedelCrafts alkylation, where there's an example of a carbocation rearrangement. So we can't do a FriedelCrafts alkylation. That means we have to do a FriedelCrafts acylation. The whole advantage of a FriedelCrafts acylation is that you get that acylium ion that stabilizes the positive charge on the carbon so you don't get carbocation rearrangements. So we'll use that FriedelCrafts acylation, and then we'll just have to reduce it in order to get rid of the double bond to the oxygen. So if this were an acyl group, you would still want the chlorine replacing the bond to the benzene ring, but you want a double bond to an oxygen there. And then you'll have AlCl3. That's the catalyst. So that's the first step. That would put this whole branch onto the benzene ring, but you don't want to keep the double bond to the oxygen, so you'd reduce it, and in this case you'd reduce it with this zinc-mercury amalgam, HCl, and heat. So those are our recipes, 2 steps to get each of those branches on. Now let's think about the order we'd have to do them in. On the left, we have a lone pair on that nitrogen. The lone pair is on the benzylic position. It's not being pulled away from the ring through resonance, so that is a strong activator. And all activators are orthopara-directing. The other branch is an alkyl group. And so that is going to be weakly activating. So that's a weak activator. And all activators are orthopara-directing. So either way, either one we do first would work. And so either one of these syntheses, either one first would count as would count as a correct answer, no matter what order you put them in. But there is one way that's slightly more efficient, and that is to put this group on first, because that's a stronger activator, so once you have that on, it'll be easier to add the second thing. If you put this on first, if you put that on first, that's a weaker activator, so it'll be harder to put on the other thing. So it's a minor thought of efficiency, but either way would work. So you'd start with your benzene ring. You would add nitric acid in sulfuric acid, and that would put the nitro group on there. You can then reduce that with that iron or zinc in HCl, and that turns the nitro group into the amine. So now we have aniline. So now we have that group there. Now if we treat this with FriedelCrafts acylation, so we'll have that acyl halide and AlCl3, we'll get actually 2 products there. So on the one hand, we will have the acyl group add ortho. On the other hand, we'll have it add para. Right? This NH2 is a strong activator. It's an ortho-para director, so we'll get both the ortho product and the para product. Now the ortho product is not what we want, so we're going to discount that. We're going to stop paying attention to that. Let's think about what we can do with this para product after we purify those 2 molecules. That's really close to what we want. We just have to reduce the double bond to the oxygen, turn that into 2 bonds to hydrogens. And you can do that by adding a zinc-mercury amalgam mix that in with hydrochloric acid and heat, and that turns this molecule into the molecule that we want. And so that's the molecule we want, and this whole synthesis is the synthesis that would give us our correct product. Okay, let's think about D. Okay, so we can go back and we can get our recipe book. So here's our little recipes, the recipes we'd want to know for this chapter. And the first thing we want to do is just assess what recipes we need to use, and then we'll think about what order we need to use them in. So to make the NH2, it's a two-step process to make this. First, we're going to need to do nitration, and then we'll reduce the NO2 using iron or zinc and HCl. So that's how we can make that. First, HNO3, H2SO4. Second, reduce it with iron or zinc and HCl. So that's how we make that. The way you put a chlorine on a benzene ring is to use Cl2 and AlCl3. So those are the recipes we need to use. Those are the ingredients that we need to mix with benzene. But now let's think about the order. Now, both of these two branches are meta to each other. They're meta to each other. The branch on top, this NH2 has that lone pair there, and so that's a strong activator, the NH2. And all activators are orthoparadirecting. The chlorine is a weak deactivator. All the halogens are weak deactivators. And that chlorine is also orthoparadirecting. So it seems like we have a problem. Both of these branches are orthoparadirecting, but we need the branches connected meta to each other. So how can we do that? Well, remember that this NH2 is actually made in two steps. And the first thing that we get is an NO2 on this position. Then we have to reduce it in order to turn it into an NH2. Well, that NO2 is a strong deactivator. But importantly, it is a meta director. So we'll need to first add the NO2. Then, once we have that meta director on, we'll add the chlorine. And then after we have the chlorine on, we can finally reduce the NO2. So we'll take benzene. We do the nitration, HNO3, H2SO4. And that puts the NO2 onto the ring. Now that NO2 is meta-directing. This is the only chance we have to put these branches on meta. So we next put the chlorine on while we still have this meta-director. Cl2, AlCl3. That adds the chlorine, meta. And now all we have to do is reduce that nitro group. We'll use the iron or zinc in HCl, and that gives us the NH2 instead of the NO2, and we still have the chlorine. and that's what we wanted. Any other order would not give us that product. This is the only order that you would do those reactions in that would give you the product you want. So first we identified what recipes we needed, and then we thought about the directing effects of each of the branches and how we can use those directing effects to get the ortho, meta, or para orientation that we want. Okay, let's move on from D. We'll look at E. And actually we have a whole bunch of these, and these are taking a little bit of time. So to avoid the videos from getting excessively long, I'm going to stop this here, and we'll pick up with E